Hello everyone, my name is Yudong Li. Normally, when you watch AI videos, people are talking about the newest, most amazing model like ChatGPT. They talk about success. But today, we are going to do something different. We are going to look at failures. The title of my presentation is Dive into Failure. Learning from ICLR 2025 rejected paper. ICLR is one of the top AI conferences in the world. Getting a paper accepted there is hard. Today, I'm going to show you two papers that had amazing idea but got rejected. Why? Because looking at how smart people make mistakes is actually the fastest way for us to improve our own work, our own project, and our understanding of artificial intelligence. Why rejected paper? The evaluation of computer science is not a straight line of constant improvement. It is a rigorous process of hypothesis, testing, and often failures. In competitive conference like ICLR, having a novel or interesting idea is no longer enough. When we transition algorithm from an experimental research phase into something that could be defended in a thesis, the evaluation must be solid. A great idea evaluated poorly is mathematically similar to a bad idea. In this presentation, we will look at two specific domains, medical AI safety and vision language diffusion architectures. Both papers attempted to solve critical problems, but they both fell into traps regarding experimental design and computational baseline. Let's begin with our first case study. The paper is titled MedFuzz, Exploring the Robustness of Large Language Model in Medical Question Answering. To understand this paper, we first need to understand the current landscape of medical AI. Over the past few years, large language models have achieved high scores on medical benchmarks like MedQA, which consists of questions from real medical exams. However, researchers have a growing suspicion. Are these models actually performing clinical reasoning, or are they simply exploiting correlation in the training data? In machine learning, we call this the clever hands effect, where a model appears to be intelligent, but is actually just picking up on superficial clues. The authors of MedFuzz wanted to test it if medical AI were truly robust. To do this, they borrowed a concept from software engineering called fuzzing, which means automatically injecting random data or mutation into a system to see if it breaks. Let's examine their method in detail. The authors designed an automated framework. Imagine you have two AI systems. System A is the target LLM. This is the medical model we want to test, acting as the doctor. System B is the attacker LLM. The attacker's job is to take a standard cleaning written medical benchmark question and slightly mutate it. The court rule for the attacker LLM is that it must only change clinically irrelevant information. For example, if the original patient in the test is a 45-year-old male accountant, the attacker might change it to a 45-year-old male bus driver, or it may change the location of the hospital. From a medical perspective, the underlying disease and the correct treatment should remain exactly the same. The hypothesis was that if the target large language model is truly performing medical reasoning, it will ignore these superficial changes. If the model changed its diagnosis just because the patient's jobs changed, it is not robust enough. On the surface, this automatic pipeline is an elegant, scalable way to test AI safety. So, why did the ICLR reviewers reject it? The fundamental issue lies in the execution of the automated attack. When you use a large language model to automatically mutate complex medical tests, you lose control. While the attacker LLM was instructed only to change an important detail, it frequently changed the clinical reality. For instance, if the attacker changed a mild fever to a high fever with localized pain, just to make the test look different, it fundamentally changed the correct medical answer. The target LLM will then give a different answer, not because it is not robust enough, but because the question was now asking about a different disease. Let's look at the mathematical and logical implication of this failure. In machine learning evaluation, we measure robustness by observing the degradation in accuracy. For accuracy drop to mean anything, we must guarantee that the ground truth label remain perfectly valid for the first fuzz input. In mathematical terms, the conditional probability of the correct diagnosis must remain constant. Because the authors completely automated the generation process without placing a human expert in the loop to verify every single guaranteed generated cross question, they could not guarantee this conditional probability. The intelligence of a student cannot be measured using an exam paper filled with contradictory questions. The major takeaway from the MedFuzz paper is about the limitation of automation in data generation. Automated data pipelines are efficient, but when you are dealing with specialized domain like medical or synthetic perturbation require rigorous human expert validation. If the baseline truth of your dataset is corrupted by the very tool you use to build it, all downstream metrics become meaningless. Human oversight is not just a safety measure, it is a fundamental requirement for constructing benchmark. Alright, let's move on to the second paper, which deals with generative model. The paper is titled From Denoising to Refiring, a corrective framework for fusion language diffusion model. To understand the problem this paper tried to solve, we must briefly review how discrete diffusion model work. Standard diffusion operates by starting with a state of pure noise. Through a Markov chain, it takes iterative steps to denoise the data, gradually forming an image or text block. However, this process is generally unidirectional under inference. If the model makes a poor semantic choice at 10-step 50, that error becomes part of the permanent context. By the time it reaches time step 0, the final output is ruined. We call this the error cascade problem. The model is trapped by its own early mistakes. The authors of Corrective try to fundamentally modify this architecture by endowing the model with the ability to look back, recognize its error, and correct them. The authors proposed a highly ambitious two-stage framework to shift from passive denoising to active refiring. In stage 1, they introduced synthetic errors into the training data. They essentially forced the model to look at corrupted drafts and train it to fix those corruptions. Stage 2 is where the architecture becomes truly complex. They implemented an online self-correlation loop. During training, the model would generate a preliminary draft. A separate frozen expert model will evaluate this draft and provide a gradient signal indicating how wrong it was. The main model would then use this feedback to revise its own output before the final loss. Conceptually, this is mimicking how a human walks, drawing a sketch, stepping back to evaluate it, erasing the mistakes, and refining the details. It is a beautiful architectural concept, but the ICLR reviewers rejected based on computational and experimental flaws. The first massive problem was the computational overhead. Training a diffusion model is already incredibly expensive. Adding an online self-correction loop means that for every single training step, the model must perform a forward pass to generate a draft, run an entirely separate expert model to evaluate, and then calculate a complex refinement loss. In computer science, algorithms must be balanced with computational feasibility. If a proposed framework requires an order of magnitude more GPU memory and compute time than, than the standard approach. The marginal improvement in image quality cannot justify the cost. Reviewers demanded proof that this complexity worth it. Beyond the computational cost, there was a flaw in stage 1 of their training process regarding distribution shift. Remember that the authors trained the model to fix synthetic errors, mistakes that the authors injected into the data. However, the artificial noise looks semantically different from the mistake a neural network makes during inference. Because the model was heavily trained to fix fake mistakes, it became highly optimized for a specific error distribution. When it was deployed for real inference and started making its own errors, the corrective framework often failed to recognize them. It is akin to training an auto-driving algorithm in a simulated video game environment. The moment it encounters the lightning of the real world, the distribution shift causes to fail. Finally, the paper failed what we call the baseline rule of empirical research. When you propose a complex computationally heavy framework that is supposed to revolutionize how vision language models generate data, you bear a heavy burden of proof. You must prove that your new method outperforms the absolute current state of the art. The authors only compared their model against older diffusion model. They omitted the comparison against the autoregressive model, which are the current golden standard for many of these tasks. By carefully selecting weaker baseline, the authors inflated the perceived value of their contribution. The reviewers recognized this and flagged the evaluation as not rigorous enough. The takeaway from Rediff is a lesson in practical algorithm design. A mathematically beautiful idea is not enough if it ignores the reality of hardware constraint and empirically benchmarking. If you introduce significant complexity to an algorithm, it must justify against the strongest baseline. Furthermore, the training environment we construct must reflect the distribution of the model we face during inference. Optimizing for synthetic praxis will lead to failure in the real world. To summarize, diving into these two rejected papers provide us with clear instruction for our own research and algorithm design. From MedFuzz, we learned that automated evaluation pipeline must never compromise human validation. From Rediff, we learned that architectural complexity must be justified by computational efficiency and proven against state-of-the-art baseline. Through these lessons, we can ensure that our future research are built on a solid foundation. Failure is not the end. It is a detour on the path to the success. Thank you for your time and attention.